going back to section 6.5, which we started but did not finish last time. So 6.5 is about the cost transform and the Dirac delta function. The Dirac delta function. Right. And so remember what the Dirac delta function was? It was this thing that did not exist for us, but it was a function that was 0 everywhere and somehow had a mass of 1 at 0. Right? So this thing somehow was 0, right? Was 0 for all x not equal to 0, and at the same time it had the integral was 1. Okay. And of course this was not possible, but we sort of wanted such a thing. And we'll see why, once we get to the next section, why we really want this sort of thing. But one way of thinking about it is that if such a function existed, we could use it to pick off values of other functions by integrating against it. Right? If such a function existed, well, then you could integrate, say, the Dirac delta function against some other function, right? And what would happen when you did that? Well, the Dirac delta function would say, I'm going to ignore everything except when x is equal to 0, right? The Dirac delta function is 0 everywhere except at x equals 0. So what you would get is the integral of only over the point x equals 0, right? Because delta is 0 everywhere else, right? And so you get this thing. Right? So it'd be sort of like an integral only over a single point. And so that would pick off, well, x is constant then, right? X is constant, it's equal to 0 there. Right? So what we would get is we get f of 0 times the integral of this thing. Right? Times the integral of the Dirac delta function, which is 1. Right? And so we would somehow use that thing would somehow pick off exactly the value at that time. Okay. Rather than some sort of average, some sort of average of that value. And this is or let me shift it a little bit. If I had something like this, x minus x naught, say, then what would this do if I shifted it? If I replaced this delta x instead by, when I change this to delta of x minus x naught, the translation of the Dirac delta function, what's going to happen then? Well, here.
We'll just pick off any location.
Right, it's going to pick off the value of f at x naught, right? Because this is going to be 0 whenever x is not equal to x naught, right? Right, and it's going to have its mass, that mass is 1, somehow concentrated at x naught. And so, this is what we sort of hoped that this Dirac delta function would do for us, but it didn't exist. And so we defined the Dirac delta function instead in terms of those d sub tau functions, right? We defined d sub tau to be like 1 over 2t, I'm sorry, 1 over 2 tau, whenever t was between minus tau and tau, right? And it was 0 elsewhere, right? And then we said, like, if we wanted, we said that, if we wanted, so recall, we did this last time, that wanted the integral of f against delta t minus t naught dt, what we meant was just the limit of the integrals as tau went to 0 of f against the d taus, right? D tau t minus t naught dt. Right, we basically said that that's how we were going to define the Dirac delta function, as something that operates as the limit of these d sub tau guys. Okay. And when we worked it out, what did we get? We got that this was at t naught, right? We got that this was the average, right? This turned out to be the average, the limit as tau goes to 0 of over t naught from t naught minus tau to t naught plus tau of f, which was the average of the function over an interval centered at t naught and in the limit that turned into f of t naught. Right. So by defining it in this way, we get something that has the property that we wanted. Right. We wanted the Dirac delta function to pick off values. Right. And this, if we define it in this way, it does. Okay.
Why is it 1 over 2 tau?
1 over 2 tau from here.
Yeah, why?
We want the thing to have mass 1. We want the thing to have area 1. So it goes from minus tau to tau and has a height of 1 over 2 tau. So the integral, right, the integral gives us 2 tau times 1 over 2 tau. Okay, so the area here is 1. Right? We wanted the area to be 1, right, because we want the Dirac delta function should have an integral of 1. Okay.
I guess I'm just confused on what happens when the limit of tau goes to 0 part of the function. Because wouldn't that mean that it'd be multiplied through by like infinity?
If you what?
Because as tau goes to 0, it means that it would be like the limit would be 1 over 0.
I mean, when you take the limit, tau doesn't become 0, right? It just approaches 0, right?
So it would just become infinitely small then.
Yes, that's true, right? But think of what you're doing, right? You're taking the average of the function, right? So you're taking if this is your function and this is t naught, right? What you're doing is you're taking the average over
And then that happens at every limit.
t naught plus tau, t naught minus tau, t naught plus tau.
And so that would be for like every tau as it approaches 0, so that would just shrink in and it would still be just the average of it.
That's right. So every one is going to be an average, right? Each one of these guys is an average value over some interval, right? So you're looking, what's the average of this interval? 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 What's the average of this interval, right? And you're looking at the number that tends to, right? That's what the limit means. The number that you tend to as tau goes to 0, right? Well, this number is the average height, right? You take the area, right? Take the area and then divide by the width of the base, right? And that'll give you a height. That'll give you the height of a rectangle that has the same area as this region. Right? That'll give you the height of a rectangle with the same area as this region, right? Which is the average value of the function, right? And well, the average value of the function, if the function is continuous, then as tau goes to 0, you're just going to end up with the value of the function, right? Because as you get closer and closer, the average value, the function doesn't oscillate that much because it's differentiable, right? So because it's continuous, and so the average value is going to tend towards this average. Danny, you looking down?
I'm still really lost. What do you mean by pick off values?
I mean that it allows you to get the value of the function at some point.
Because I thought this is like, if like the height doesn't exist, like, I think I might be confused from I thought there was like an infinite height or something.
Yeah.
But the picture you just drew is a finite height.
So
I don't see the relationship between those two pictures.
they're not related. They're not related.
So then,
They're not related. This thing is d sub tau, right? This is a picture of d sub tau.
okay.
Okay.
I thought that was
This
the,
is a picture of f.
I thought that was the Dirac function.
This is the thing that we're using to, these guys are what we're using to define the Dirac function. So the Dirac function is going to be, if we're talking about the Dirac function integrated against something, what we're going to mean is that the limit of these guys integrated against that function as tau goes to 0.
So we're multiplying those two graphs together? So we have the d tau and then the f.
That's right. So you're multiplying these two graphs.
Because that's like the base and the height or something like that?
That's right. So this will do the averaging for you, right? Because when you hit this graph with this, if you multiply this guy by that guy, well, what's going to happen? It's going to chop off, right? It's 0 out here, right? So it's going to chop off your function, right? Right.
I think I was confused because I thought you said the Dirac function doesn't have a height necessarily.
That's right. It doesn't, right? Because it's,
But this does.
these guys
You're
do.
putting the height
but
of
as-
f, not the.
So then what's the point of the Dirac function?
To chop off.
Point of the Dirac function, at least for us now, is just to you use it to integrate against a function and get some value, get the value of the function at a point. Okay, but you'll see something better in a second.
Okay.
You'll see that it actually is a necessity. Okay. Or another way of thinking about the Dirac delta function is that as they in the title of this chapter. They say it's about impulses, right? So you have a differential equation, and you have some forcing function, and at some point, the forcing function has this big impulse applied to it. Okay, and the Dirac delta function is to model that, right? Something huge happens just at one instant in time. Your girlfriend knows. So, yes.
So is the d sub tau just a form, as close as we can get to the
That's
Dirac
right.
function?
That's
Because
right.
the Dirac function doesn't actually exist.
That's right.
Okay,
So
so that's why the one we're using has a finite height, even though that.
that's right. And so in the limit, we think of the limit being the Dirac delta function.
So can we compare this relationship between the two, to the fact one is real, to the Heaviside function and then the t sub?
So it's a little bit different. The Heaviside function, right, is rather you have off, and then something turns on and goes on for an infinite period of time, right? And further, the thing that turns on is not an impulse, right? It's simply some sort of constant value that's applied,
Okay.
right? So this is something different, right? It's some sort of impulse that's applied at an instant, right? And yeah, it's to model an instantaneous impulse, right? Rather than a switch that's being flipped.
Okay. I mean more in terms of the relationship between these two functions and the relationship between those two functions.
Say that again.
So the relationship between the Dirac delta function and d sub tau, and then the Heaviside function and tau sub c.
So,
I'm just trying to relate it to the previous section. But I don't know if that's appropriate.
yeah, it's not, I mean, it's a little bit different. It's,
Okay.
rather think of it as something
Something
rather different.
Okay.
Okay. Okay. Okay. So, if we use the Laplace transform on it, suppose we take the Laplace transform of shifted Laplace transform. If we take the Laplace transform, then maybe you see immediately what happens. What is it? Well, we get the integral from 0 to infinity of this thing, and it's e to the minus st dt, which is, yes,
Would you just get e to the minus st naught?
that's right. We're going to get e to the minus st naught. E to the minus st naught.
So, like the intermediate steps and all of that would be that you would substitute the d sub tau,
That's right.
and then insert the, and then you just do the limit of it.
It's the same thing. You do the same thing. In fact, but we've already done it.
Yeah,
Right.
it's just the same steps.
Right? Just call this e to the minus st. Like, and then you're going to get e to the minus st, evaluate it to being t naught. So at this point, the Dirac delta function is just going to be just another thing that we use. We'll have some differential equation. You have some differential equation, and then you solve it. Like it's just another one of our functions for which we have a to add to our dictionary of Laplace transforms. Okay. In the next section, when we talk about convolution, it will become clear that the Dirac delta function is actually something a little bit more unusual. Although that won't be central to our discussion. Anything else?
I'm kind of confused as to how this is different from just like plugging a value into a function. Like, is it like in a case where you're given an integral and you're trying to, like I'm just wondering in what case you would need to do this whole process. If you're given like a function f, could you just plug the point that you want into the function?
Suppose you don't have the function. Suppose somebody gives you a sound, say, right? And right, it's maybe you're not able to tell what the value of that. You're not given the function explicitly, but you're only able to integrate the function. Say, well, then how do you figure out the values of the function? Well, one way would be to take to chop off. Maybe you can chop off bits of the integral and average them, right? So, it's in the case that you don't have the function that this makes sense. Okay, just wait. It will become clear that its importance will become clear in just a few minutes. I guess, Brett?
It's kind of similar to the canonical delta function.
No. It's not. It's also a delta function, but it's not the same function. So the canonical delta function, that's more of a notation. Right? If you say like deltas of ji defined to be 1 if equals j and 0 sort of like a convenient notation to use, but that's not related to Dirac. Okay, so let me just do as usual, I'll do an example, and this example will actually be pretty illustrative of we use the translation and modulation laws that you will need on the exam. Should be instructive. So here we go. Y double prime plus 1/2 y prime plus y equals, say, the shifted Dirac delta function, and let's let y and y prime is 0 to be 0. Okay. As usual, you take, you know what's going to happen. You take a Laplace transform, these things are set up so the constants match, right? So when we take the Laplace transform of y double prime, we're going to get s squared Laplace transform. Here we're going to get 1/2 as Laplace transform. And here we're going to get Laplace transform, right? And here we get e to the minus s, because we get e to the minus s times t naught, the t naught is 1. Okay. So we get y then is 1 over s squared plus 1/2 s plus 1 times e to the minus s. And as usual, we use the completing the square. So we get, this is 1 over s plus a quarter squared plus 15/16. And recognizing that this is something like the sine, the Laplace transform of the sine, we want this to be like a over s squared plus a squared. Right? So let's put in an a here. Root 15 over 4. 4 over root 15. Right, so that this thing is in the form. Okay. And so the Laplace transform, the inverse Laplace transform of this then is going to be 4 over root 15 of the inverse Laplace transform of e to the minus s. I'm going to write it like this, tau sub minus a fourth of root 15 over 4 s squared plus 15/16. I'm taking this thing is I'm taking the shift out. I'm writing in terms of the shift. Okay, because we want to use the translation. Yes?
I thought some of the book the book usually just uses the Heaviside function. Is that wrong to write like u negative 1/4?
If you just write u negative 1/4, I mean.
You do that once you've already taken the inverse Laplace. Would that be confused?
Yeah, I mean, you could put it in, right? I mean, you could put it in, but I'm not going to.
Okay.
But you can't, you still need to put this in, right?
Yeah.
Yeah, because this thing indicates the shift, and the Heaviside function just indicates the cutoff. So this turns into this turns into 4 over 15. Sorry. This e to the minus s turns into a translation. The modulation turns into a translation when you run it through the inverse Laplace transform. Right? And this thing here is then e to the minus t to the 4 sine right, and then that's the end. Then you shift it. 4 over 15, e to the minus t minus 1 over 4 sine 15 over 4 t minus 1. use of 1, 2.
Is it e to the negative t minus 1/4, or is it t minus 1/4?
Negative quantity t minus 1/4. Right? Because you're shifting this thing. You're shifting the variable. Right? So this t will become t minus 1.
So like, going back to when you decided to complete the square, I'm just sort of curious, because like this happened in the homework.
Yeah.
How do you sort of decide when you're going to complete the square and when you're going to use partial fractions? Obviously here, this doesn't break up nicely, but
That's the point. Yeah. So if it doesn't reduce,
okay.
right? So if it reduced into linear terms, then you would use partial fractions, right? But this is as far as you can go.
Well, because anything that reduces, I mean, couldn't you just use partial fractions with that also? Or sorry, anything that you could use partial fractions, couldn't you just complete the square with also?
Could you do that also?
You should like always be able to complete the square, so I was just sort of, I don't know what to use.
I see what you mean. Yeah. I think so. And then it should yield the same answer. It should yield the same answer. I think. Awesome.
I'm just a little bit confused on the different like steps of the shift. So like you have e to the minus s in the first step, and you have the shift of t tau negative 1/4, which I understand that part.
Yes.
But then moving from that to the next step, how do you take the inverse Laplace of like e times this other function? Is it just the inverse Laplace of the e function times the inverse Laplace of that, or like
No.
is the e the shifting portion?
So let me write down. So remember we've got these things with the inverse Laplace transform of the inverse Laplace transform of e to the minus some modulated some e to the minus cs times a function, right? Turns into translate inverse Laplace transform like that, right? And then we have this other one, the inverse Laplace transform or translate. Turns into the modulation of the inverse Laplace transform.
Okay, so the reason that we still have the e exponent in there is that like the e is it's not the same e as in the first step.
That's right.
Okay.
It's a different one. So this e to the minus s turns into the translation,
Okay,
right? This translation turns into the modulation. Right? That was the goal, right? That modulation turns into translation. Translation turns into modulation. Right? So here we've got modulated translated function. So we're going to end up with translated modulated function. Right?
And is there a difference, because like I don't remember seeing, do they have the translated notation like that in the book? Because I only ever remember them using the Heaviside function, and I'm just confused if there's any difference between that.
It's just a notation, right? The translated guy is defined to be the function t minus c times u sub ct. Right. That's how we define the translation, or that's how they define the translation. So I don't remember. It may be that the book writes everything in terms of the Heaviside function, but for me, I think for me it's clear to think like this, that modulation.
Yeah, it
and
makes sense. I
translation.
just haven't seen it in an example. Is it okay if we write it in terms of that?
Yeah, of course. Yeah. Okay, enough of the Dirac delta function. Now let's go into the most important thing, convolution. So, Dirac delta function. So the Laplace transform and convolution. two functions, f and g. We define f star g, which is called the convolution of f and g. We define it like this. F star g at t, it's a function, and its value at t is going to be the integral from 0 to t of f of t minus alpha g minus g of alpha b alpha. So we sort of run one function backwards and one